Hi, I'm Paris Scaris, and this is Lab 3, Magnetic Field of a Bar Magnet for Physics 2212. So just a quick introduction to this lab. The purpose was to use field and calculated values to determine the distance dependence of the magnetic field created by a bar magnet. The materials used were a small bar magnet, a magnetometer app. In this case, I used a Teslameter, a ruler, a smartphone with a magnetometer sensor, and tape. The benefits of this lab are that it allows students to visualize and observe magnetic fields and also to understand how magnetic fields are affected by distance. So the procedure for setting up the lab involved a few steps. In step 1, we set a magnet and a ruler on a flat surface, with the poles of the magnet laying orthogonal to the true north-south axis. Step 2 involved laying the phone vertically as shown, and then using the magnometer app on the phone to find the position of the phone's magnometer sensor. Tape was then laid on the phone following the top edge of the ruler. In step 3, we repeated step 2, but this time the phone was laid horizontally, and the intersection of this tape marked the location of the magnometer sensor on the phone, as shown in step 4. This is a summary of the part of the lab where the data was collected. Using the marked location of the phone's magnetometer, the location of the magnitude of the magnetic field was found for specified values of 20 microteslas, 70 microteslas, 120 microteslas, 170 microteslas, and 220 microteslas. In order to measure the off-axis magnetic field, we had to use the distance for which the magnitude of the magnetic field was 100 microteslas, and the net magnetic field of the magnet was found in relation to the magnetic field of the Earth. The two images shown below, steps 5 and 6, depict the way that the off-axis magnetic field was found. In this case, the two vectors, d_perp, created a right triangle. The resultant vector d is the total distance of the sensor from the magnet. Shown here is my data found during the physical part of the experiment. During this part, we used the phone's magnetometer sensor to find the magnitude of the magnetic field created by the bar magnet at different field strengths. One thing I found is that the distance from the magnet increases, the magnitude of the electric field decreases. On the left in yellow are the magnitudes of the electric fields and the location of those fields. The values in blue are the averages of the values in yellow. On the right is a logarithmic plot of the magnetic fields and the distances. You can see that there has been a linear line fit to the data that has a slope of negative 6.444 and an intercept of negative 21.385. I have explained the experimental data from this lab. Now this is a summary of the calculated data from my lab experiment. Here we have a couple of important equations. The first one is the Biot-Savart law for the magnetic field of a dipole. The second one is the distance dependence equation for the magnetic field. Taking the logarithm of both sides of the distance dependence equation gives us the equation of a line that compares the magnitude of the magnetic field to the distance from the magnet. This is equivalent to the equation of the best fit line from the graph shown earlier. From my findings, the average magnitude of the magnetic field was 8.73328 times 10 to the negative 5 teslas. From the equation for K, I was able to find that mu is equal to 0.00258 amps times meter squared. In GlowScript using Python, I created a computational model that depicts the on-axis and perpendicular magnetic fields. The teal arrows represent the perpendicular magnetic fields, while the orange arrows represent the on-axis magnetic fields, and the red arrow represents the magnetic field 45 degrees from the axis, and the white cylinder represents the magnet. Listed underneath the computational model are the values for the perpendicular and on-axis magnetic fields, the value of the magnetic field 45 degrees from the axis, and the distance from the magnet. So just some questions that can be answered as a result of this lab. The computed 45-degree distance value was the same as the observed 45-degree measurement, and this means that the experimental portion of the lab was successful because the values were the same. If I hadn't oriented my experiment to compensate for magnetic north and laid out the ruler at some intermediate angle with respect to Earth's magnetic field, the magnitude of the magnetic field at any distance would be inaccurate because the Earth's magnetic field would always interfere. And by compensating for magnetic north, the interference from Earth's magnetic field was negligible. If two identical magnets were stuck together end to end, the magnitude of the magnetic field would be in the same direction, but increased by a factor of 2 because there were two magnets. Thank you.